So this block diagram reduction rule. Okay. In this topic, we basically discuss about different reduction rules that will help us in solving a given block diagram network. Okay. So using these rules, what you can do is you can reduce a system consisting of n number of blocks into a single block. And once you have the single block, you can simply find its transfer function by dividing the output signal with the input signal. Okay, so let us discuss these rules in detail. Okay, and this is very important from exam point of view as well as from competitive exam point of view. All right. So in your final exam, these rules may be asked for somewhere between 4 to 8 marks. Okay. So there are about 10 rules. Let us discuss one after the other. All right. So first rule, indirectly, we have already studied. Okay. So I would say rule number 1 as reduction of minor feedback loops. Okay, so this is your first BDR rule. Okay, now in your block diagram, if at all you encounter such a scenario wherein you will find a comparator, okay, connected to the forward path transfer function and the feedback transfer function in this manner. Okay, if at all the main block diagram is consisting of such an arrangement. Okay, this can be plus or minus such an arrangement. So what you can do is that you can reduce this entire block diagram. Okay, so this block diagram is consisting of a summer, forward path transfer function block, and a reverse or feedback path transfer function block, right? So you can replace all these elements with a single block consisting of the overall transfer function. So other day we had seen that for a closed loop feedback system, the overall transfer function is G of S divided by 1 plus or minus G of S into H of S. And this is your input R of S, and this is your output C of S. And remember, we use plus sign for negative feedback and minus sign, we are going to use it for positive feedback. Okay, so this is your first reduction rule. Okay, reduction of minor feedback loops. Okay, all right. So like this, you have different rules. Okay, let's discuss rule number 2. So rule number 2 talks about the reduction of blocks connected in cascade. Okay, so I would say combining blocks connected in cascade. Okay, so sometimes it is also called as series connection. Okay, what do you mean by series connection? Feed forward connection. Okay, so let's say suppose in your main block diagram you encounter such a scenario. You have some block G1 which is connected to some block G2 in this manner. Okay, and let's say the input signal to this block is some X1. Okay, so what is the output signal of block 2? Input signal into block transfer function. So the output signal, okay, where I have placed the question mark, there you are supposed to write the expression for output signal. And what is it gonna be? The output signal X1 into G1. So I can say this signal is X1 into G1. Okay. And this X1 G1 is given as input to block 2. And block 2 gives an output of X1, G1, and G2. Okay. So this is the output of this particular cascaded system. Okay. So if you inspect closely, the output is consisting of product of individual block gain. So that means to say, whenever you have the blocks connected in cascade, what you can do is you can reduce two blocks into a single block, and the single block is consisting of overall transfer function, okay, which is nothing but multiplication of individual transfer function, or the product of individual transfer function. So this is the input X1, okay, and let's say this is your output Y. Okay. Even if you clump the two transfer functions, okay, what are you going to get the output as? X1 into G1 into G2. So output going to be X1 into G1 into G2. Right. So you can clearly observe that in both the cases, the output remains the same. Okay. So that's your rule number 2. Reduction of blocks connected in cascade. So in the similar way, if you have 3 blocks, let's say G1, G2, and G3 connected in cascaded manner, the overall transfer function going to be G1 into G2 into G3. All right. Fine. Just a minute. Okay. Rule number 3. So rule number 3 is something to do with parallel connection. So let's write combining blocks connected in parallel. Okay. Now, let's say in our block diagram, okay, we have this scenario, okay, something like this we have. Say you have some block G1 and you have some block G2. Okay. So let's say some signal X1 is coming in. Let's say output of this summer is Y. Okay. So let's say you have this parallel connected block scenario in your block diagram. Okay. If at all you have a connection of this kind, how are you going to inspect the output? What exactly you are going to get the output? That is what you are supposed to inspect. Okay. Let us put an addition sign here also. Okay. Now let us see what is the output. Okay. So X1 is the incoming signal. So the same X1 is being given to the block G2 as well, right? So this also receives X1 signal over here, and this also receives X1 signal over here. Okay. Now the output of block G1 is X1 into G1. Similarly, output of block G2 is x1 into G2. Okay. Now, at this summer, x1 G2 is getting added with x1 G1. So the output is equal to x1 G2 plus x1 G1. Okay, or you can say output Y is equal to x1 times G2. Observing that whenever the blocks are connected in parallel, the overall transfer function is nothing but addition of individual block gains. Okay, so your individual block gains are G1 and G2. So the overall gain becomes G1 plus G2. So when you have, such a connection, what you can do is you can simply replace, okay, this whole network with a single block consisting of the net block transfer function, that is G1 plus G2. And this is your input signal X1, and this is your output signal Y. So what is Y? Y is simply X1 times G1 plus G2. So X1 times G1 plus G2. So you can clearly observe that, in both the cases, okay, in the actual case as well as in the reduced case, you see that the overall transfer function or the output of the system is not altered. Okay, so the output is intact, you can say. Okay, so this is your parallel connected, rule. Now, there are some special cases. Okay, let me discuss the special cases over here itself. Okay. Let's say suppose you have block arrangement of this kind. This is your summer. Let's say somewhere here you have addition sign, and somewhere here you have, let's say, subtractive sign. This is your output. Let's say this is your input. So what is the output in this particular case? Very easy to, obtain the output. So output of the top block going to be x1 times G2, and output of bottom block going to be x1 into G1. Okay. Now this is a summer, right? Which algebraically adds the signal. Okay, the first signal x1 G1 is having a positive value. On the other hand, the top signal, it's having a negative value, hence it subtracts the second signal, right, from the first signal. So it becomes x1 times G2, or the net output signal is G1 minus G2. Okay, so whenever we say blocks connected in parallel, not necessary that you should, just take out the addition. I would say you're supposed to perform algebraic addition. Okay, algebraic addition, in the sense, you will have to consider the sign as well. Okay, so please take care of the sign whenever you reduce the blocks connected in parallel. If both the signs are positive, it is G1 plus G2. If one of the sign is negative, then it is G1 minus G2. If both the signs are negative, then minus of G1 plus G2. Okay, so this is one special case, say special case A. Okay. Then we can also discuss another special case. Okay. Because if I don't discuss this now, then you are likely to commit errors when you solve the problems. Some G2 you have. what I will do, this case 2, let me discuss when we consider the problems, okay, because that is going to be little, confusing. No problem. Fine. So rule number 3 is done. Let's go to rule number 4. Okay. So rule number 4 is something to do with the, summing point shift. So let us say shifting of summing point after a block. Okay, shifting of summing point after a block. Okay, what do you mean by this? Okay, to understand this particular rule, okay, first let us create a small block diagram. Okay, let's say you have a summing point of this kind. So let's say some signal x1 is here and some signal x2 is here. Okay. And let us consider this as plus or minus. Okay. Fine. Now, this is your, say, output. Okay. What is the output for this particular case? As you can see, x1 is given at the top side of the summer, and x2 is given at the bottom side of the summer, and this x2, or to that matter x1, can be additive or subtractive in nature. Okay, for simplicity, let us consider additive only. Okay, so what is the net signal coming out of the summing block? It is x1 plus x2, right? x1 plus x2. So what is the output of block G? That is y. So y is equal to G times x1 plus x2. Okay. So this is the output in as it is condition. Okay. Now over here, what we are trying to discuss is shifting the summing point after a block. Okay. So the summing point is over here. Okay. Sometimes in block diagram reduction, okay, we see that if you can shift the summing point, okay, behind a block, then we will get some easy reduction rules. Okay, so for that reason, you will have to understand this particular rule. Okay, you will understand when you try to solve a bigger block diagram. Okay, fine. Now the summing point is over here. What I am trying to do is that I'm trying to shift this particular summing point after this block G. So if I shift the summing point behind, okay, G, so my new block diagram looks something like this. Okay, so this x1 is directly given to G, right? And after G, you are going to find the summing point. Okay, and to this summing point, okay, you have to feed signal x2, and this will be my output. So what I have done, I have simply shifted this summing point behind the block G. Okay, so this move is called as shifting the summing point after a block. Okay, now if I simply shift the summing point, okay, will it affect the system? That is what you are supposed to see. See, whatever you do, you should see to that before or after the movement of summing point, the output signal remains the same. Okay. Now we have moved the summing point behind block G, right? Due to which the summing point has come and occupied this particular location. Okay. Let us inspect the output. So output of block G is x1 into G, and the signal which was connected to this summing point is x2. So what is the output of this summing point? It is x1G plus x2. Okay. Now check your output. Before shifting, your output is gx1 plus gx2, right? Your output is gx1 plus gx2. But after shifting the summing point, your output has become gx1 plus x2. So what is missing in your output? This g term is missing. This g term is missing. So in order to maintain the same output, okay, in both the cases, what you have to do is you have to do a small manipulation. So over here, what you have to do is you have to multiply this signal x2 with g. Right? If you multiply signal x2 with the g, the summer will receive a signal g into x2. So your output becomes gx1 plus gx2. Okay. So whenever you shift the summing point after a block, okay, the signal gets multiplied with g. Okay. Shifting the summing point after a block should be incorporated with a multiplication of g. All right. So that's your rule number 5. So rule number 4. So rule number 5 will be the vice versa condition of rule number 4. So that means to say, what if you were to shift a summing point before a block? So let us write shifting of summing point before a block. Okay, before or ahead, one in the same. Okay. Let's say suppose you have this particular scenario in your block diagram. Okay, fine. So this is the given circuit, and you are supposed to shift this particular summing point before the block G. Okay. Now, to do that, first what we will do is we'll try to find out the output Y in as it is condition. Okay, as you can clearly observe that the output of the top block G going to be x1 into G. So the signal value is x1 into G, and here the signal value is x2. So your output is basically x1G plus x2. Okay. Now what we have to do is we have to shift the summing point, okay, ahead of block G, but your output should remain the same. Okay, let's see whether we get the output, same. All right, so this summing point is placed over here. Place the summing point. Now this summing point will receive the signal x1. Okay, and since you have shifted the summing point before this block G, so the block G placement is somewhere over here, and this is my output. Okay, and to this point we are connecting signal x2. Okay, so just like that we have moved the summing point before G. Now let's see, with this movement, are we getting the same output or not? Okay, so if you get the same output, then you can say, Okay, the valid step we have carried out. Okay, now this is x1, right, and this is x2. So output of the summary is x1 g, right? But in your original network, your output is just x1g plus x2. On the other hand, after shifting the summing point before the block, in your output, you are seeing this alien term, right? So G is the foreign term here, which shouldn't have been there. But it is present because of your shifting of the summing point. Now, how do I cancel out this particular G term? It is possible to cancel out this particular G term, provided you multiply the signal x2 with 1 by G. So if you multiply the signal x2 with 1 by G, then what happens is that the signal value at the bottom half of this summer becomes 1 by G into x2. And your output y, then it becomes, okay, so this is x2 by G. Okay, so what it becomes? x1 into G plus x2 by G into G. So G gets cancelled, hence you will be left with signal x2. So you can say that before and after, the output signal is not changed. So the output signal is remaining the same. Okay. Before a block invites sage. Okay, so summing point after block is G. Summing point before block is 1 by G. Okay, so this way you can probably memorize. So it is sage, if you remember, that's more than enough. Okay. Sixth rule. So far we discussed about the summing point. Okay, now let's discuss about the takeoff point. Okay. So write down moving a takeoff point or shifting a takeoff point, one and the same. Moving takeoff point after a block. Okay. Now, what do you mean by takeoff point? Okay, takeoff point is nothing but the signal tapping point. Okay, the tapping point of the signal itself is called as the takeoff point. Okay, let me tell you what exactly of this kind. Say some signal x1. Let's say this is your y. Okay. So this is called as takeoff. So this is called as takeoff point. Okay. Now, what we are trying to do is that, okay, we are trying to shift this takeoff point after block G. So that means to say what kind of output we are going to get. Okay. Before that, in as it is condition, okay, let us evaluate the output. So the output is x1 into g. Okay, x1 into g. Now what we will do, we will shift the takeoff point as shown. So this is your block G. Was is found. So this is my output. Okay. Now, what's the output? So input is x1. So output y is basically x1 into g. Okay. But since we have shifted the takeoff point, okay, after block G, what happens is that in the bottom path, the signal value doesn't remain x, right? Because what is the signal value after block G? The signal value is x1g. And the same signal, you're carrying it forward, right? So the signal value, okay, at the bottom path, it becomes x1 into g. Okay. So what is the signal value in the bottom path? Before shifting the takeoff point, it is only x1. But after shifting the takeoff point, the signal value has become x1 into g. So that means to say you have altered the signal value, which you are not supposed to do it. So how are you going to correct it? So you will be able to correct it provided you multiply this signal x1g with 1 by g. If at all, if you have had multiply the output signal with 1 by g, you would have obtained the bottom signal as x1 itself. Why? Because input to this particular block is x1g, and therefore the output of this block is basically 1 by g into the signal x1g. So gg gets cancelled, and you're going to get the signal value as x1. Okay. So whenever you move a takeoff point after a block, what do you get? You get the manipulation as 1 by g. So this is the reverse procedure of summing point shifting, right? When you shift the summing point after a block, you know, the manipulation, what you have to do is you have to multiply with g. On the other hand, if you move a takeoff point after a block, you will have to multiply with 1 by g. You know, 4 subrules you can easily write it down. Okay, so that's the reason I said in the beginning. It is sage. Summing point after is g. On the other hand, takeoff point after the block is 1 by g. Okay, so this is point number 6. 7th rule. So obviously, before a block. So moving takeoff point before a block. Okay. So let's say suppose you have this scenario. Okay. And what you are trying to do is you are trying to shift this takeoff point before this block G. Okay. So before doing that, let us try to find the output in as it is state. So X1 is the input. So output of the top block is X1 into G. And the same signal is being carried forward, right? It is like you have tapped the output. So how much you are tapping? You are tapping X1 G units, right? So this is X1 into G. All right. Now, once you move this particular takeoff point, okay, in front of block G, okay, what kind of signal value you are going to get that we are supposed to evaluate. So the takeoff point is being shifted here, and this is my Y, and this is my X. So output of block G is still X1 into G. So that is fine. But what about the signal value? In as it is state, okay, the signal value in the downward bar is basically X1, right? Is basically X1. Just a minute. Okay, thank you. To attend the call. Yeah. So in as it is case, the signal value is X1. But what is that you are supposed to get? You are supposed to get the signal value as X1G. But instead you are getting X1. So what manipulation you have to do? You have to multiply this bottom signal with G. Okay, so incoming signal is X1. So output signal going to be X1 into G, that is G into X1. Okay, so this is what you have to do. Okay, in case if you think of shifting a takeoff point before a block. Okay. So the eighth rule is about interchanging the summing point. Okay, see, not necessary that rule 8 should be the interchanging of summing points. Okay, so you can mix it up, no problem. So this seventh rule could be your rule number 1, and so on and so forth. It doesn't matter. Yeah, just make sure that all rules you are incorporating while writing the answer. Okay, so rule 8 is interchanging summing point. Okay, so sometimes we see that in order to apply block diagram reduction technique, it is convenient to interchange the summing points. Okay, so how do you do that? Okay, so to understand the interchange of summing point, what we will do is we will consider a small block diagram scenario. Say some x3, some x2, some x1, okay, and signal 1. Okay, now interchanging summing points. Okay, interchanging summing points in the sense you are basically interchange this summing point with this and vice versa, or vice versa, right? This you bring it over here. Okay, now before doing that, okay, first let us evaluate the output in as it is condition. Okay, so for summer 1, for this particular summer, the output signal is x1 plus x2. Okay, and for summer 2, the positive signal is x1 plus x2 and the negative signal is x3. So output is x1 plus x2 minus x3. Okay. Now, in interchanging summing point, okay, what we do is we basically interchange the signals along with the sign. That means to say signal x2 with sign plus is exchanged with signal x3 with the negative sign. That means to say when you interchange the summing points, you have to interchange with the signal value, right? So what I'm going to do is I'm going to push this x3 to summing point 1 and push this x2 in place of summing point, in summing point 2. Okay, so x3 we are shifting it to first summing point and x2 we are shifting it to the second summing point. When I do that, will I be able to get the same output? So that is the point under consideration, right? Whatever you do, you make sure that the signal value is not altered. Okay, so in as it is condition, the output is x1 plus x2 minus x3. Okay, by interchanging the summing points, you are supposed to get the same output. Okay, are we getting or not? Let us investigate. So x3, we are pushing it, right, in place of x2. So this is your x3 now. Okay, and in place of x3, you have what? You have x2. And remember, x2 has a positive sign, so same sign I am keeping. Okay, and over here x1 you have. So output of first summer is x1 minus x3. Okay, so x1 minus x3 is given as input to the second summer along with x2. So the output of second summer is x1 minus x3 plus x2. x1 minus x3 plus x2, or you can also say that y is equal to x1 plus x2 minus x3. So you can observe that the output is not at all changed. Okay, so you can interchange these summing points. Okay, without altering the output of the summing point. Okay, so sometimes you find this particular rule very much useful. Okay, but there is a special case that the two summers should be directly connected to each other. Okay. In a sense, there shouldn't be any block in between the two summers. Okay, as you can clearly observe that between block summer 1 and summer 2, there are no blocks in between. Okay, if at all there is a block in between the summing points, then you cannot think of interchanging the summing points. So always remember, you can apply these rules in block diagram reduction technique, provided you find exact replica, okay, in your main block diagram. There shouldn't be any alterations. Okay, if you find the exact replica in your main block diagram, then you can think of applying all these rules. If not, no, you can't apply. Okay, so that's your rule number 8. Okay. And then finally we have rule 9, which is called as splitting a summing point. What do you mean by splitting a summing point? Okay, that means to say a single summer can be splitted into 2 or more summers. Okay. Let's say you have a block diagram scenario of this kind. Say some x3, some x1, some x2. So this is minus, this is plus, and this is plus. And this is your output. Okay. So splitting means, this particular summary is consisting of 1, 2, 3 signals. Okay, probably we can break this particular summary into, 2 summers. Okay, sometimes, this particular splitting will help in identifying the minor feedback loops, etc., etc. Okay, fine. Before doing that, first let us try to find the output signal y. So y is equal to x1 plus x2 minus x3. So x1 plus x2 minus x3. So based on this, equation, you can probably split the single summer into 2 summers. Okay. Say suppose this is my x1 and this is my x2. Okay, so the output of first summing point gives you x1 plus x2. And if you add x1 plus x2 with negative x3, you will get the overall output as x1 plus x2 minus x3. So as you can see, in both the case, the signal value is unaltered. Okay. And you can also derive rule 10, that is merging the summing points. Okay. So basically there are 8 rules. So merging the summing points in the sense, it is vice versa. At all you have 2 summing points, you try to get a single summing point. Okay. So vice versa condition. Okay, fine. So that completes block diagram reduction rules. Okay, so don't worry. We just discussed about the rules. Okay, we did not discuss about the reduction. What you say method. Okay, now in problems, you will be given with a block diagram consisting of 8 blocks or 10 blocks or 12 blocks. Okay. Now, all these, let's say for example, your given block diagram is consisting of 12 blocks, and you will be asked to apply BDR technique to obtain the transfer function. In the sense, the 12 blocks you need to reduce into a single block. Okay. Now, how are you going to reduce? You are going to reduce to a single block by applying, the following rules. Okay. Sometimes you may apply 3 or 4 rules. Sometimes you may have to apply all the 10 rules. You never know. Okay. So that is where, these block diagram reduction rules comes into picture. Okay. Fine. So what we will do is, I will consider a very simple problem. Okay, very simple problem. And with this simple problem, probably I'll be able to explain the block diagram reduction rule. Okay. So first, let us consider problem number 1. Okay. Let's say suppose I have this particular problem. Okay. So write down the question. Obtain C of S by R. Obtain C of S by R. Okay. So how are you going to solve this? So if you see there are 1, 2, 3 summing points, then 2, 4, 5, and 6 blocks, right? So in the end, what you have to do is you have to obtain a single block which will have an input signal R of S and an output signal um, C of S. Okay. So how are you going to solve? Okay. So always remember one thing: whenever you apply the block diagram reduction rule, okay, try to keep it simple. In the sense, this is the general, um, steps to be followed while solving a block diagram reduction problem. Okay. Step 1 should be something like try to reduce. Okay, try reducing. Um, something like series blocks, comma, or bar parallel blocks. Okay. So try to reduce. whether any series connected blocks or any parallel connected blocks in the system. Okay, and then okay, you can think of applying, you know, reduction of minor feedback loops. Okay, so this is what you're supposed to do in block diagram reduction technique. If let's say you don't have any series or parallel connected block or any, you know, reduction of minor feedback loops, then only you can go for, if no moves are available. Okay, moves as in step 1 and step 2 are available. If you don't find any series or parallel connected blocks, or if you don't find any minor feedback loops, okay, then you can think of applying the other rules of BDR technique. Okay, if no moves are available, then only apply the remaining rules. Okay, but always remember, when you apply the remaining rules, you know, you try to get the series blocks or minor feedback loops by applying the remaining rules. Okay, now if you look at the given problem, okay, you see that there are some series blocks and there are some parallel blocks. For example, I see some parallel block over here. Let's say this is my step 1, and what is this? Parallel block. Okay, then I also see um, some series blocks here, right? So let's say this is my move to, and what is it? Series block. Okay, so first let me reduce this parallel and series block. So when I reduce the series block, okay, what do I get? I get the, and then you will have, I think the visibility is bad, so let me use black pen only. So into G2, all right. And the parallel reduction yields, okay, you can see the sign, right? This is plus and this is minus. So the overall transfer function becomes G3 minus G4. Okay, and then there is H1 here. And then there is a summing point over here. Okay. Now, can you see? There is a feedback loop here, right? So there's a minor feedback loop. It is a negative feedback loop. Okay, this is my step 3. So this is feedback loop. So if I reduce the feedback loop, what do I get? So what is the reduction formula? C by R is equal to G divided by 1 plus GH, right? Okay, G of S divided by 1 plus G of S into H of S. So let me apply that. So by doing that, you can see that, you know, I'll be able to eliminate one summing point and 2 blocks, right? So my overall transfer function is G of S. So G of S is nothing but G1 into G2 divided by 1 plus G of s into h of s. So it is G1, G2, H1. Okay. So this summing point will disappear now. So you're left with the outer summing point and a second block, which is having overall transfer function as G3 minus G4. And this is C of S. This is R of S, the negative side, and the feedback path. Right. So what is that you're observing? You're observing that, these two blocks are connected in cascade. So step 4 is nothing but series blocks. So what do you mean by series blocks? You will multiply, say, this block transfer function with the other block transfer function, right? So here, block 2 doesn't have any denominator, so obviously the numerators are getting multiplied. So you're going to have G1, G2 into G3 minus G4 in the numerator. And in the denominator, you will have 1 plus G1, G2, H1. Okay, and this is your block. Okay, and you're going to have a summing point over here, R of S, and this is your C of S, right? And this is your feedback. Okay, this is plus and this is minus. So what do you see here? You see a feedback, minor feedback loop, right? This is your G of S and this is your H of S. So H of S is 1 over here. So what you can do is you can reduce this entire block diagram into a single block, okay, consisting of one input signal R of S and one output signal C of S. And what is the overall transfer function? C of S by R of S is nothing but G divided by 1 plus GH. Okay, so let me write it here. So C of S by R of S is equal to G of S. So G of S is this whole term, right? G1, G2, G3 minus G4 divided by 1 plus G1, G2, H1 divided by 1 plus, because it is negative feedback. So for negative feedback, you get 1 plus in the denominator, right? Into G into H. So again, repetition of numerator, G1, G2, G3 minus G4 divided by 1 plus G1, G2, H1 into H of S. What is H of S? H of S is 1. So if you simplify, what you get is something of this kind, right? So this denominator gets cancelled. So in the numerator, you have G1, G2, G3 minus G4. And in the denominator, you will have 1 plus G1, G2, H1 plus G1, G2 into G3 minus G4. So this is your transfer function. This is your transfer function. So this is the answer. Okay. So this is how you solve the block diagram reduction technique problems. Okay, this is the simplest problem, just for the demonstration purpose I have used. Okay, so in the future classes, okay, let's solve more complex problems. so that you will be able to understand all the rules. All right. So I extended by 10 minutes. Let's meet tomorrow.